I want to start it off with posting two questions. Actually, the first one is, who has heard of a successful artificial intelligence project? Just raise your hands. Really? I mean, he mentioned like a dozen. No? Really? Are you so shy, or is it really true? You haven't heard about successful AI projects? Like AlphaGo, for example? Everybody should have heard of, right? Second question, this is the last one. Have you heard of any unsuccessful AI project that failed completely and people lost tens of millions of dollars? Wow, one hand, that's something. Two? Three? Oh, I'm surprised, I thought that would be kind of zero. So. Where does the current hype of AI come from? What do you think? The reason is actually quite simple. When you have a success, you talk about it, right? You make a press release, you give TV interviews, you do all kind of stuff, you write magazine articles and so on and so on. That creates the hype. If you fail, you won't do a press release, right? Very rarely, I guess. And worse than that, if you fail in an AI project, you not just failed, you look like stupid. Because you failed in an AI project, right? So you're too dumb to implement a successful AI system. So there's a double motivation not to talk about it. By the way, I just realized I'm also not so smart. I need this device to, yeah. Thank you very much. And how do I do? Green button, I guess. Yeah. All right, so what I want to do, since there's all this hype, and I think that's one of the reasons why many of you are here as well. You heard about AI and you need to get some kind of informed what's going on in your industry, especially in the finance industry. But you barely ever hear any speeches about failures of AI and where the problems really are in AI. And there's very few subjects that people usually talk about. It's mostly, deep learning. You probably all have heard about bots, chatbots, stuff like that, robo-advisors, 3-4 subjects. That's pretty much it. So people usually don't go into any more detailed artificial intelligence technologies. So I will focus just on deep learning because it's probably the most popular subject around these days. And people talk about self-learning, all these powerful machines that do all these crazy kind of cool and intelligent things. It's kind of true, kind of not true. I will focus on the not true part. Just one word about myself. So I'm one of the few surviving dinosaurs in that space. I mean, you can tell by my age, right? I've doing this since 35 years. So that's, I guess, longer than half of this room attendants are old. So, I've seen it all. I've seen all the ups and downs, and this time we have a huge upswing, and trust me, there will be a downswing. It depends on when it's going to happen, and it depends on, what kind of players are entering the market and what job they do. Right now, the market is dominated by all these big companies, the Googles and the Facebooks and Apples of the world. The future, however, in my eyes, is in companies that you've never heard of. Very, very small, early stage, beginning companies that just enter the market and that will not rely on all these, deep learning and open source kind of tools that are around there. They will invent their own tools. And this will be one of the key topics in my masterclass I will do after the break. So be invited to join. Hopefully I'll tell you something that is new and not something that you've already heard 20 times. So I've written a lot of books and blah, 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 but what is most important, I think, and what I'm most proud of is I've successfully, and I want to stress that, implemented over 100 AI projects, systems, products all around the world in 3 continents. And the average talker about AI, they have done maybe 0.5 projects, right? So it's quite an asset I think I have, and it helps me to see through, is there substance into something or not, and I can pretty much very quickly tell that's good, that's bad, you know. So, and I want to talk about pretty much the bad side. I don't need to talk about all this, you know all this. You may have heard about that Dubai is going to launch the first, or they already have trials, the first drone taxis. Soon they will be completely autonomous. You can fly around, you know, you just put in where you want to go and then off it takes, and hopefully it deposits you where you should be. You know, I always say it's a bit cheating, right? It's in Dubai, you know. There's like 5 streets in Dubai. That's about it. And everything around is sand, you know. So how difficult is it for the drone to find the right spot? You know? Try this in Kowloon, right? It's not going to work. So, but you know, there's enough of these systems out there, and I have to say, some stuff is cool. A lot of stuff is completely overhyped. For example, like Siri, all these Echo device, these kind of things don't really work that well if you really use them on a daily basis. And you know, the trends in the electronic devices with robots is very, very strong, especially in Japan. I think in the next few years we'll see a lot of cool stuff there. So that's the positive side, that's it. One slide, no more. So I want to talk about this mostly. You know, as an introduction to this, I think one of the biggest issues in that whole space, in that whole AI space, is there are very, very few knowledgeable people out there. And I'm not saying that to pump me up, it's a fact, you know. Try to hire someone in Hong Kong that has 5 years of experience in AI. 0, you know. So that's a big problem. So these guys that enter the market are in their 20s, early 30s maybe, when they're old. They have no clue about AI. You know, they call themselves experts when they have looked at a book from a meter distance that says AI on it. It's horrible, I'm telling you. It's very difficult. And it's all over the world like that. So companies invent all kinds of tricks to hire people that have some kind of an AI background. Very few companies have the abilities to train the people in-house. And also it will take time, right? It's costs, it's not really efficient to do. So it's a major problem. And a lot of the issues I'll talk about come from that fact. There's just not really experienced AI people out there. You know, it's like in the crazy days of the stock market, right? When the stock market went up and up and up and up and up. And the guys that entered the market, they only knew one trend, right? Up. They never had seen a crash before. So when the crash happened, they all freaked out, you know? Jumped from the towers, you know, stuff like that. And a similar thing will happen here in AI. I predict this, you know, in a couple of years. So I put this slide in to scare you a little bit. So I don't know how familiar you are with mathematics, but if you entered university, you should know that. No. You shouldn't laugh. You should know that. I'm deadly serious about this. So this is differentiation of a function. It's very simple. You have a differentiable function. So differentiable essentially means it's smooth, right? It has no edges or stuff like that, or it has no gaps. So like this one there. And then to differentiate means to find the optimum values in that function. So where's the top and where's the bottom? And you do this, and that was an invention of Newton and Leibniz at about the same time, 300 years ago, more than that actually. And how to do that is just to put a straight line on this function and just move it around. And when the angle of the straight line is 0, it means it's horizontal, then you have some kind of maximum. It doesn't have to be an optimum, but it is a maximum, right? You can see here, for example, this is a maximum. In the whole neighborhood, there's no higher value, right? But it's not the global maximum. The global maximum is here, right? You see that? So the problem with this is it is the basis of deep learning. I'm serious. So the deep learning is 300-something years old. It's not something that has just been invented. It's just hyped now, but it's not really anything new. So what deep learning networks are doing is essentially you train them by showing them examples. You show an example A and you say, okay, if I show you that, I want this output. If I show you another example, I want this output, right? Classical examples, you show pictures of cats and dogs. You say, this is a cat, this is a dog, this is a cat, this is a dog. You do this 1,000 times, right? Until this stupid stuff gets it. And then we'll be able to say, okay, this is a cat, this is a dog. Usually, it's very easy to cheat on these things. So, but to do this, you define an error function. And this is what this is supposed to be. You say, okay, look, I reward you when you have a right answer, and I punish you if you have a wrong answer. And that defines an error function. And what you try to do is try to find the minimum of this error function, right? The least mistakes you make. So that's all of what deep learning is. Nothing else, really. It's very simple stuff. So I spoke about that local and global minima. That is the error function. And the problem with these deep learning networks is that they normally do not find the global minimum. They usually get stuck in these local minima, and there's all kind of tricks and ways to get them out of these local minima, but in pretty much any practical application, you get stuck in some local minimum. But the problem is, when the problems are very complex, you don't know whether you are in a local minimum or whether you are in a global minimum. You can't tell because you kind of don't know the future, right? Where are you really? So that's a huge theoretical problem. When you have a neural network, you've trained it, you don't really know how good you are. Even though the error in any direction you move will increase, will get worse, right? You think, wow, I got it. It's not true. You can just be stuck in one of these local minima. And if you, and this is just a two-dimensional function, right? If you have a realistic application, you don't have just one output of the network. You may have 5, 10, hundreds. So you don't have a two-dimensional scape, you have a three-dimensional scape or a 100-dimensional scape, which we cannot visualize. But imagine when the arrow landscape gets more dimensional, like from the black and white to the color ones on the bottom, the landscapes get much more complicated. So what can happen is, if you're lucky, like on the left side, you start at some random point with your training, and then you smoothly sail down to the optimum minimum value, the valley, so to say. But realistically, when you start anywhere in such a rugged landscape, imagine you're in the Alps or somewhere, right? And I drop you at a random place somewhere. It is somewhere on a hill, probably somewhere in the middle. It's not going to be on the peak, or it's not going to be on the bottom if I do this just randomly, without any guidance, without any knowledge how the mountain looks like. Imagine you're blind, right? And I put you in the mountainscape. What are you going to do? So you have a stick, you stick around, and you want to find the valley, and you go where the stick goes the deepest. Right? And you guide this, you do one more step, and you start again, put the stick around you, and where's the steepest decline you go. But there's no guarantee whatsoever that it finds you the bottom of the valley. And this is shown in this chart here. So it can be anywhere, and you can actually end up on some plateau, which is the biggest problem for these kind of networks, where every move is pretty much doesn't get you anywhere better. It's just, plus minus zero, there's no real progress. You get stuck. The worst areas for these deep learning networks is kind of so-called plateaus, flat areas, no ups and downs. Where you go, the stick trick doesn't work anymore, right? And that is one of the biggest problems for these neural networks, and there's no mathematics how to resolve this. It doesn't work with these kind of models. And another big problem is when you learn, what you have is a set of data. Antoine mentioned that, right? You have a set of data that you train on, and then you have another set, an independent set of data that you test it on. And you don't want to mix them, so you don't train on the data that you're testing on, right? That would be stupid, it would be cheating. So what you need to do is, you have a set of data, which are these blue round dots here, just randomly distributed somehow, and you try to find the best fitting curve, that gives you the least distance to all the dots. So on the left side, you take a very simple approach, and that's actually what the prior models, so-called perceptron kind of models, did in AI. They just draw kind of a straight line. It's called a linear approximation, right? It's actually, if you count the difference right and left, it's actually not too bad, surprisingly. You have some that are on top and some off the bottom. If you average it up, it's quite okay. You approximate very good. But in a reality case, it doesn't really help you much, right? To put a straight line to your data set, it's usually nonsense. So what you can do, you can improve this a little. Instead of having a horizontal line, you kind of change the angle to get a bit better hit. But then you make a major step, and that's where the modern neural networks come in, the deep learning networks. You do a non-linear approximation, so not a straight line, but a curve, but a differentiable curve that is kind of smooth, right? So you're getting quite good. However, if you do the optimum solution, which is the last one, that hits so the red line, right, that hits every spot that is there, every data spot, 100%. So you have zero error. You can't get better. That's the absolute best solution to your problem. But now think about what happens. If I have a new point, chances are it's not on this crazy curve. It's somewhere off, right? You might be much better off to have the second best solution on the left, which doesn't really fit every training example. Right? This kind of sounds like a contradiction, but think about it. It's quite obvious, right? Especially with this example. So what that means is another huge problem. You have to ask yourself, how long do I train this network? Do I train it until it has no more error? No, it's not. Because what this means that this network has just learned by heart, so to say, all the points. It doesn't generalize. It doesn't abstract. It doesn't say, oh, I got it, the trend is like this. It's more like, oh, I remember A, I remember B, I remember C, and so on, right? It's like learning by heart instead of understanding what's going on. So this is probably one of the worst problems for neural networks because there's no solution to that. Nobody can tell you when to stop training a neural network. It's a really tough problem. And another thing is so these were all theoretical problems. Now, a few practical problems. When you have experience with these neural networks, the algorithm is so that you have to train the network in a certain phase. Then you test it on some test data, and then you put it live. And while it's live, while it's running and doing its job, you cannot train. Deep learning networks are batch processes. They have to separate the training process from the application process. There's some, first beginnings trying to change that, trying to make it continuous learning, but that creates another problem, In most applications, trust me, you don't want to have a continuous learning system because something can happen that influences the training live. So all of a sudden, the system behaves completely different. It may be correct, but the system is like in chaos theory. It might need some time to adjust to the changes. It has to adjust all the weights, all the settings, and so on and so on. And in this adjustment period, it may have complete nonsensical responses to your inputs. So that's a huge problem, the batch processing part. And the other part that relates to the theoretical part before is nobody can tell you how long to train. So 1 day, 2 days, 100 days, until the error is very low. We just learned that the error very low is not a good way to do. So people are completely lost. And the only thing that really helps here is you have experience. You kind of feel it, in your belly. Doesn't look so good, we have to train a little bit more. That's really how it works. It's not science, it's an art to do this stuff. And imagine if you use this in a live trading environment or so, it can kill you, in seconds. So you have to be really careful when you use this technology in live financial applications, especially in real-time financial applications. I can tell you that I was one of the first quants, in the 1980s, right? we did this. I actually was the first one in Europe to apply neural networks to do Bund future forecasting for German Commerzbank. And it was quite successful from the results. But it wasn't deployed. And you know why? Because the managers didn't understand it. And it's actually, to me, I was so offended. I thought, what the hell, I just showed you how many % better you do when you use the system. They said, yeah, but we're making a lot of money. That's not so interesting. What is much worse if this thing fails? One day, it caused a crash or something. Then what? We can't even explain why. It just happened, and then what? Well, we all get fired, so they didn't deploy it. Today, it's more like, oh, let's try, see what's happening. So the mood has really changed, I tell you. And another area that usually is a slide I always show when I talk, because that is nearly a knockout criterion for using deep learning. You see two sets of images, right? On the very left side, a car, a leopard, and like a Indian pyramid. And on the left side, you have some loudspeakers, an insect, and a dog. So when you look at these pictures, opala, what happened? That wasn't me. I'm serious. Can you start again? Yeah, great, thank you. Did I cause this? No. Okay, so just look at these pictures here. Do you see any difference between this picture and this picture? You can, right? Because they are set up the way that you can see it. So our eyes' resolution is too bad to see the difference. But there are differences, pixel differences. And the difference is actually quite a lot. If you see them, they are highlighted here in the middle for all these pictures. So you can see the difference pictures, right? If you black out the background, you can see really that there are differences. But if they are overlapped with these pictures, you won't see any difference. So for any human, these pictures on the right and left, and for both sets of pictures, are the same pictures. However, what you can see on the bottom is the classification of a deep learning network. The pictures on the left are, after certain training, are classified in the correct way. Pictures on the right are all completely nonsensical classifications. The neural net says to all of them, this looks to me like an ostrich. This is nonsense, right? And why is that nonsense? Because the problem for us is, if we see pictures that are identical or close to identical, there could even be some minor changes there that we notice. The response of the network should be very similar or identical, right? If the pictures look the same, response should look the same. But not, one time you see it, it classifies correct, and then other times it comes up with some complete nonsensical things. So why is that important? Think about security applications. Think about biometrics, face recognition, right? So what you can do if you know the structure of the neural network, you can make any picture, like the car or the leopard or whatever, make the network believe it's something completely different. So it looks at my face and it would say, oh, okay, you can pass, you're the chairman of Pricewaterhouse. That's not such a good thing, huh? So this is very, very critical. You can manipulate any deep learning network that way. Think about that. Any deep learning network can be manipulated that way. If you know the structure of the network, you can find out how to cheat, how to modify the input to give a completely different output. For any security-related application of neural networks, that's a knockoff criterion. And this doesn't only work for optical applications, it also works, and more scary even, for sound. You can mix ultrasound into a normal voice command. So if our ears have a certain range, right? Beyond that, they can't hear anything. Ultrasound, for example. We can't hear bats when they fly around, when they do their echolocation, for example. We cannot hear this. So, because it's unaudible to us, we can mix this into the voice signal, and no one will notice. No one will hear a difference. Now think about you have an echo device or something similar. You know, now in China, it's a huge upcoming industry. There are about 1,000 companies in China right now. They're trying to build competing devices to the Echo voice recognition device, right? You know all these Echo, I assume, right? It's not available in Hong Kong yet, but in America and Europe, you have this. You have a device in the kitchen or so. You can say, hey, Alexa, or whatever it is, order me a pizza. It will recognize that, execute the transaction, pay, and then hopefully soon you get one pizza, another 100 or so, and everything is fine. But with this technology and with this insight, you can put ultrasound on top of it that causes completely different actions. Right? So for example, you can say, Alexa, order me a pizza, and suddenly all the lights go off. Or whatever you want to do. So again, when these devices use deep learning for critical functions, you'd be very, very careful with this. There's one really funny story from Germany in the past that explains another major problem. And it goes to explaining the functionality of these networks. And it's called Clever Hans. Have you ever heard about Clever Hans? Oh, you do? Cool. Probably his name is Hans, I guess. So. But this is Clever Hans. It's a horse. That was in the 19th century, around pretty much exactly around 1900 to 1903. It was a sense, at that time, there were not really much cars, right? So everything was still, horses, and there were thousands of horses in every city. And then all of a sudden, a guy came up, and he claimed he has a horse called Hans. And that horse is extremely smart. It was able to do basic calculations, additions, multiplications, subtractions, even divisions in simple cases. But not only that, it could also answer, everyday questions like, what weekday is it today? And people were shocked, and this guy, became a millionaire by traveling around and showing Hans. And obviously, all the people were very skeptical. They thought, there's some cheat there, right? Something's not right. This guy has some tricks, doing this. So people tried to figure out at that time, what's the trick? What's happening here? How come this horse can calculate? And then they thought, okay, the guy, is the trick, right? He does something to the horse so that the horse finds out what to do. So what they did, they replaced the guy. Just put someone from the street doing the same thing. Ask the horse, what is 5 plus 3? And to the surprise of everyone, the horse still was correct 90% of the time. Pretty much always correct. But obviously, it didn't take too long to figure out what's going to happen or what's happening there. The horse was really very smart, but in a different way. It smelled and it felt the reaction, subliminal reaction of the person that asked the question. So if the guy, for example, asks, what is 3 plus 2, right? And then the horse used his toes to tap, right? And it started tapping and tapping, and what did I ask? 3 plus 2. At 5, it would stop. And it figured the right answer out by just reading the guy subconsciously. So, if you expect something, automatically you do like, not so obvious, but, you have some little kind of body movement. And this horse was so smart to really read exactly when to stop. So it didn't get anything, right? It didn't know how to calculate anything, but it knew its master, or it knew the person that asked the question, how to look at this person, how to watch to do the right thing. And this effect we have in deep learning also. So I always show this example because it's so unbelievable that I have to show it. I have no other choice to show this. Read what this says. Neural network learns to identify criminals by their faces. You know, you laughed before, now you should laugh. Because this is just the biggest joke. And it's so embarrassing to science that, you know, you would want to leave the neural network area because of that. How in hell can they seriously say, I can recognize a criminal by their face? You know, I always mention that, you know, I'm German. You know, the Nazis had these kind of theorems, right? They say, oh, he's a Jew, he's not good, you know. Crazy stuff. How can you recognize criminals by their faces? You can't, right? Because criminal, what is a criminal is a cultural question. It's not a genetic question. You know, Adolf Hitler was the worst criminal in modern history, right? He killed millions and millions of people. I mean, there were others doing similar things, but you know, for a German, it's really a very, very bad time in history, and you don't want to get close to this, right? So, but in Germany, everybody thought he's the hero. He's the leader of the company, you know? The young kids followed him. So, is he a criminal? It depends, right? Where you stand, on what side of the line you stand, in what culture you live. And he's just one example. You can go through all of history, you'll find lots of these examples. What defines a criminal is the culture in which you live. It's not your genes, right? But they say, oh, we see this in their faces. And it gets worse. Once they got challenged, you know, they invented face features that justify their result. So the outcome was, they said, okay, we now found, really, what is the feature in the face, actually? You know, it's the distance of the tip of the nose to the tip of your upper lip. It's shorter in criminals than it is in the average population. Can you believe this? I mean, seriously. And what always like knocks me off the stage is, look at the bottom. This was accepted and reviewed by the MIT. I hope you all know what the MIT is. It's just unbelievable, literally unbelievable. But I can resolve that issue. It's the clever Hans effect. You know what happened there? You can think about it. It's very, very simple. What they did is they used about 2,000 photos to train the network. And they said they have an accuracy rate of like 90%, better than humans, right? So the system can recognize criminals better than any humans. I mean, obviously, sure, because it's nonsense. So what happened is, you know, if you have 2,000 pictures, you divide it half, to be fair, half and half criminals, half non-criminals. So the non-criminals pictures to get is easy, right? You go to the internet, Facebook or wherever, you easily get thousands of pictures. But how do you get pictures of criminals? Any idea? Anyone here criminal? Raise hand. You won't get pictures of criminals, right? You won't. It's not, there's no online portals for criminals showing their faces, right? So how did they get the pictures for criminals? They got them from the police. Where else? Or the government. You know, they made a deal. Give me 1,000 pictures of criminals. So what kind of pictures will you get from the police? You get normalized pictures, right? Like passport pictures. Face straight, glasses off, no smiling. And you have to show both ears. You know, stuff like that. And they put you in front of a meter scale, right? So they can see your height. And the light is always coming from the right side, and the background wall is white. This is what the neural network found. It realized, oh, lots of these pictures, you know, they have the same background. Yeah, that's it. That's the solution. It's crazy. Clever Hans, but in a very stupid way, I have to say. Think about this. These are problems you really find. I mean, this is obvious to figure out, right? But you know, I don't know if you heard about, just recently, Stanford University has announced that they can identify gay people by their faces. Gay people. Think about that. You know, a lot of Arabic countries have laws against being gay. You go in jail. So if this gets in the wrong hands, right, it's just catastrophic. And no one challenges this because it comes from Stanford University. Yeah? They should merge, MIT and Stanford, they should. So I have seen all this and I got so upset and I thought, what the hell is going on? So I made up some fake science myself. You know, I wrote an article. I constantly write articles on my LinkedIn page, and you're invited to go there. I have like 30-something AI articles there on my LinkedIn page. So I thought, I got to check out how far can I go with this, right? So I published an article, it looks like this, and I say, Darwin finally proved wrong by AI. And why did I do this? Because I wanted to hit two birds with one stone, right? There's so many people out there that claim to be AI experts. They're popping up everywhere. I mean, literally everywhere, you know. And they are like in their mid-20s, and they say they have 35 years of AI experience. So I thought, no, I'm going to shoot at them. So in this article, I write, there's a famous scientist, this is his name there, Professor Dr. E. Calf. If you look at the name, maybe you realize something. And he's from Harvard University, not Harvard, right? So I have like 100 of hints like this in this article. But the funniest thing is I put in there is that the gist of this discovery of this Dr. Calf is that he found out that some people among us, they can switch their genetic expressions just by thinking. Right? So a person like that can think, I want to be an AI expert, and bang, he's an AI expert. And stuff like this, completely crazy. So I published this. It's the most downloaded article I've written ever. And I'm telling you, I mean, to defend the public audience, about 40% got it, right? They said, wow, super funny, you know, crazy German humor and blah, 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 stuff like that, right? But about 60% either asked me, wow, interesting, can you get me the email of Professor Calf? No, where is this institute, you know? Where in Boston is it, you know? You know, I need to know more. Others writing me, I knew it all the time, that, you know, Darwin was always wrong, you know. I mean, it's shocking. I mean, literally shocking. And I invite you to read it. I mean, in my eyes, it's hilarious. It's very funny. So, as I said, I have more stuff on my LinkedIn page. If you want to contact me, please feel free to do so. So now, to wrap it up, you know, I'm working for Pricewaterhouse now, and I would never have thought I would do this. You know, not with Pricewaterhouse, but with an audit firm. You know, I used to be a CEO for many years of public US companies, you know, and auditors are not your friend, believe me, you know. So I never thought I would end up working for an audit firm, but I found out it's actually quite interesting and fun. We do some really, really cool stuff. And I don't need to explain to you what Pricewaterhouse is and who they are, but this is the stuff I'm doing there right now. And it's really cool. You know, we started in the cybersecurity space. You know, my background is actually also cybersecurity. I'm not only pioneer in AI, I'm also pioneer in cybersecurity. I wrote the first book in Europe about computer viruses, and even about how you can use neural networks to detect self-modifying computer viruses and stuff like that. I did this in the early 1980s, 1985, just after the computer viruses were detected. So one of the first areas is to use, you know, Pricewaterhouse is one of the key cybersecurity advisors in the world. So we're trying to figure out completely new ways on how to deal with cybersecurity incidents. And you know now the biggest threat is IoT attacks, right? You're not using any more attacks for servers and firewalls and stuff, but you're trying to get into through IoT devices that are barely detected. And then the question is, how do you get from one IoT device to another? And think about what I said about this subliminal messages in voice and visual commands. So this is some of the interesting areas we are discussing. But then obviously as an audit firm, we're doing a lot in the area of automation of audits, legal stuff. It's very tricky. But for example, I've been, as I said, CEO of a public company in America, and every quarter you have to write a report. And in the beginning, these legal reports are very similar, but quite different. But if you go on, you barely notice any difference anymore between the first quarter report and the third quarter report. You copy them pretty much. You just change the numbers, and if the number switched more than like 5%, then you add a line of command. That's pretty much it. So areas like this, are open for automation, I think. So this is an area. And then obviously the whole fintech area, blockchain, ICOs. I mean, the hottest topics in fintech right now. We're getting heavily involved in this, and for example, one of the most interesting areas is smart contracts, right? Smart contracts are neither smart nor contracts. So how do you verify that a smart contract is really doing what you want it to do? It's a very difficult mathematical, logical problem. So these are some areas we get involved in. And as I said, sorry, I forgot to mention, so if you want to contact me, please contact me directly, or our CTO is a very smart guy, Andrew Watkins. So we work very closely together on solving these problems. So as I said, I'm giving a master class. So this was all very critical about AI, right? But I'm not a critical person, otherwise I couldn't have survived like 35 years in AI. I have my own theories how the future of AI will look like, and I will talk about a wide range of areas from ants to quantum computing, even to computer conscious. So feel free to join me. It's just across here, the next room, a quarter after 11. Thank you very much for your attention.